This is Unit 2.2 in Aerodynamics 1, Lift Production and Drag. Objectives are to cover lift, drag, thrust, and flight control systems. The terminal objectives for Lesson 2.2 remain the same. Be sure to read the enabling objectives for this lesson located in your textbook. There are four forces of flight: weight, lift, thrust, and drag. Weight is the force of Earth's gravity acting on the mass of the aircraft. Lift is a force that acts primarily against weight. Lift is an aerodynamic force. Thrust is the force produced by a jet engine or an engine-propeller combination. Drag is the force that primarily acts against thrust and retards aircraft motion. Drag is an aerodynamic force. Equilibrium flight exists when the sum of all moments and the sum of all forces around the center of gravity are equal to zero. The example on the right, my thrust and drag are equal to zero, and my lift and weight are equal to zero. An aircraft does not have to be in straight and level flight to be in equilibrium. In this graphic, the aircraft is climbing, but it is not accelerating or decelerating. In a climb or descent, equilibrium occurs when lift equals the perpendicular component of weight and thrust is equal to the sum of drag plus the parallel component of weight. All other flight conditions are non-equilibrium or accelerated flight conditions when opposing forces are not balanced. Accelerated flight will cause either changing airspeed, changing direction, or both. Examples of accelerated flight conditions are takeoffs and turns. During the takeoff ground run, thrust exceeds drag and a small amount of friction, and weight exceeds lift. At liftoff, lift exceeds weight, thrust still exceeds drag as the aircraft accelerates. The aerodynamic center is the point along the chord line where all changes in the aerodynamic force take place. It is approximately 25% aft of the leading edge, which also corresponds to the maximum thickness of an airfoil. Aerodynamic forces are forces that are the result of pressure and friction distribution over an airfoil. Lift, the component acting perpendicular to the relative wind, and drag, the component acting parallel and in the same direction as the relative wind. When airflow strikes the leading edge of an airfoil, it slows to near zero velocity, which is known as the leading edge stagnation point. Dynamic pressure will drop due to decreasing velocity. Static pressure will be nearly equal to total pressure at this point. The airflow then accelerates as it leaves the leading edge stagnation point due to a decrease in the cross-sectional area of the stream tube. The airflow will reach its maximum velocity at the point of maximum thickness of the airfoil. Maximum velocity corresponds to the minimum static pressure and the maximum dynamic pressure. Behind the point of maximum thickness, airflow velocity will decrease until it reaches the trailing edge of the airfoil, where it is nearly zero. This creates another area of high static pressure called the trailing edge stagnation point. For a symmetric airfoil, the acceleration is identical on both the top and bottom of the airfoil. That is, at a zero angle of attack. This produces a symmetric pressure distribution that produces zero net lift. For a positively cambered airfoil, meaning that the mean camber line is above the chord line, the acceleration is greater on top. This means that at a zero angle of attack, a positively cambered airfoil will produce lift. The aerodynamic force equation is 1/2 rho v squared, or Q, times the surface area times the coefficient of that force. We know that our two aerodynamic forces are drag and lift. Since lift and drag are the perpendicular and parallel components of aerodynamic forces, they are functions of the same factors. So we can see here that the only difference between our lift equation and our drag equation is the coefficient. Our lift equation is equal to 1/2 rho v squared times the surface area times the coefficient of lift. Within the coefficient of lift, we have compressibility, aspect ratio, viscosity, angle of attack, and camber. An acronym to remember this is CARVAC. If all other factors remain constant, an increase in density, or being at a low altitude, will cause an increase in lift. What we also see is that an increase in velocity, if all other factors remain constant, will cause a more rapid increase in lift. That is due to velocity being squared. An increase in wing surface area would also produce greater lift. This would be an example of how to decrease surface area. The pilot has direct control on three factors within the lift equation. That is velocity, camber, and angle of attack. Camber and angle of attack are found within the coefficient of lift, and velocity is found in the lift equation. As angle of attack increases, the coefficient of lift increases to a maximum and then begins to decrease. The peak of this is called CL max. Any angle of attack beyond CL max AOA will result in a stall. In straight and level flight, as angle of attack is increased, the pilot will have to decrease velocity to maintain level flight. What we see is that angle of attack and velocity are inversely related in the production of lift. Increasing the camber of an airfoil causes coefficient of lift curve to shift up and to the left. CL max increases, but CL max AOA decreases. Zero angle of attack produces positive lift for a positively cambered airfoil. Zero lift occurs at a negative AOA for a positively cambered airfoil. Decreasing camber has the opposite effect. Drag is the component of the aerodynamic force that is parallel to the relative wind and acts in the same direction. The drag equation is the same as the lift equation except for the coefficient of drag. As angle of attack increases, the coefficient of drag increases. There are two types of drag. Parasite drag is not associated with the production of lift. Induced drag is the drag associated with the production of lift. Total drag is simply the combination of parasite drag and induced drag. Parasite drag is divided into three different types: form drag, friction drag, and interference drag. Form drag results from separation of airflow from a surface and the low pressure wake that is created by that airflow separation. Form drag is reduced by streamlining or reducing the size of the component. Friction drag is the retarding force formed due to the interaction between the airflow and the aircraft surface. Friction drag can be reduced by painting, cleaning, waxing, polishing, and flush-mounted rivets. Interference drag is created from the mixing of airstreams between components of the airplane. Examples include the fuselage to the wing or the wing to the hanging components. Interference drag is reduced by fairing and filleting. Parasite drag is equal to QF, where F is the equivalent parasite area. F represents the size of a flat plate that would generate the same amount of parasite drag as the airplane. As velocity increases, parasite drag also increases. Infinite wing. High pressure airflow moving up around the leading edge of the airfoil is called upwash and tends to increase lift by increasing the average AOA. Airflow moving down around the trailing edge is downwash and tends to decrease lift by decreasing the average AOA. On an infinite wing, upwash and downwash would be equal. This would produce a zero change at the aerodynamic center. Since there is no such thing as an infinite wing, we must account for airflow that flows around the wingtips, creating vortices, also known as wingtip vortices. This airflow is not accelerated over the wing, so it does not create lift. As these vortices flow downward and flow at the upper portion of the trailing edge of the wing, the airflow around the wingtip effectively doubles the downwash. The additional downwash results in a net downwash at the aerodynamic center. The increase in downwash causes the average relative wind to be inclined compared to the free relative wind. The total lift vector is then inclined aft, since it must be perpendicular to the average relative wind. The total lift vector has two components. The effective lift is perpendicular to the free relative wind. The induced drag is parallel to the free relative wind. Induced drag is the portion of total drag that is associated with the production of lift. The equation for drag induced is on the right-hand side of the screen. Notice that lift and weight are interchangeable because in equilibrium flight, lift is equal to weight. Wingtip devices. They reduce vortices by helping to inhibit airflow around the wingtip. Examples are missiles or missile rails, wingtip fuel tanks, or winglets. Ground effect occurs as a result of a reduction in induced drag when an aircraft is operating within one wingspan of the ground. Wingtip vortices gradually become inhibited from completing the rotation cycle around the wingtip due to the airflow hitting the ground. The reduced downwash allows the total lift vector to orient more vertically and reduce the induced drag. When landing, the decrease in induced drag results in increased effective lift, decreased total drag. During takeoff, as the airplane leaves ground effect, it will experience decreased effective lift and increased total. Induced drag varies inversely with velocity squared. Induced drag varies directly with angle of attack. Lift to drag ratio. The lift to drag ratio is used to indicate the efficiency of the airfoil. By simply placing the lift equation over the drag equation, we can cancel everything except for the coefficient of lift over the coefficient of drag. Maximum lift to drag ratio, LD max, AOA, and airspeed. The peak of the LD curve is called LD max. LD max AOA produces the minimum total drag. Parasite drag and induced drag are equal. LD max AOA produces the greatest lift to drag ratio. LD max AOA is the most efficient angle of attack. Total drag is the sum of parasite drag and induced drag. The lowest total drag is also the point of the greatest ratio of lift to drag, called LD max. Total drag initially decreases as velocity increases until reaching LD max, and as velocity increases beyond LD max, total drag then increases. In summary, this is what we discussed for the first part of Lesson 2.2. Next, we will discuss thrust and power curves. For the thrust and power curves, we have some general assumptions. All curves assume standard day equilibrium flight, fixed pitch variable speed turboprop, no afterburner for a turbojet. Power curves represent work per unit of time. Turboprop thrust available. Thrust available is the amount of thrust that the engines are producing. The thrust available is dependent on power control lever setting, or PCL, velocity, and density. The propeller can only accelerate air to a certain velocity, so as speed increases, there is a decrease in thrust available. This does not occur with turbojet thrust available. A ram effect increases mass for thrust production, also known as a free lunch. Maximum thrust available occurs at full throttle at low altitudes. Power available is the amount of power that the engine is producing. power available is dependent on PCL setting, velocity, and density. Maximum power available occurs at full PCL and low altitudes. Turbojet power available is a straight line. This is because thrust available is constant, while velocity constantly increases. Maximum power available occurs at full throttle and low altitudes. Thrust and power available are determined by the engine and propeller combination. Shaft horsepower is equal to the engine output. Thrust horsepower is equal to the propeller output. The T6B produces 1100 shaft horsepower using the Pratt & Whitney PT6 Alpha TAC 68 turboprop engine. The ability of a propeller to convert engine output, shaft horsepower, into thrust horsepower, is determined by its propeller efficiency. Propeller efficiency is simply thrust horsepower over shaft horsepower. Thrust horsepower is always less than shaft horsepower due to friction in the reduction gearbox and drag from the propeller. The T6B has a variable pitch, constant speed propeller that rotates at 2000 RPM. In equilibrium flight, total thrust must equal total drag. The thrust required curve is the amount of thrust that is required to overcome the total drag in equilibrium flight. LD max is the same location on both the total drag curve and the thrust required curve. LD max AOA is the minimum total drag and the minimum thrust required. As airspeed increases greater than LD max airspeed, induced drag decreases, but parasitic drag increases at a greater rate. This increase in parasite drag requires an increase in thrust. As airspeed decreases below LD max airspeed, AOA must be increased to maintain level flight. The resulting increase in induced drag and total drag requires more thrust than at LD max airspeed. Power required is the amount of power that is required to produce enough thrust to equal total drag in equilibrium level flight. Thrust excess is the difference between thrust available and thrust required. Since turbojet thrust available is constant, maximum thrust excess occurs where thrust required is at a minimum, which is LD max AOA. Turboprop thrust excess. Thrust excess, once again, is the difference between thrust available and thrust required. If a thrust excess exists, you will either climb or accelerate. Maximum thrust excess for a propeller-driven aircraft occurs at a velocity less than LD max and an angle of attack greater than LD max AOA. Maximum thrust excess occurs at the slower velocity due to the drop in thrust available prior to reaching LD max velocity. At max power, and when thrust available equals thrust required, the airplane has reached its maximum velocity in level flight. For the T6B, this is 255 knots of indicated airspeed at sea level. Power excess is the difference between power available and power required. If a power excess exists, you will either climb or accelerate. For a propeller-driven aircraft, maximum power excess occurs at LD max velocity and LD max AOA. Turbojet power excess. For a turbojet, maximum power excess occurs at a velocity greater than LD max and an AOA less than LD max AOA. Increased weight requires you to increase lift. To increase lift, you must either increase AOA or increase velocity. Increase velocity and weight increases both parasite and induced drag, requiring more thrust and power. Thus, the thrust required and power required graphs shift up and to the right. Thrust available and power available are not affected, and both thrust excess and power excess decrease. Altitude effects. With a constant weight and lift, the velocity must be faster at a higher altitude. The net total drag will be unaffected, so while the thrust required shift is to the right, the magnitude of thrust required remains the same. However, power required shifts up and to the right due to the increase in velocity. Both thrust available and power available decrease due to the reduced air density. Both thrust excess and power excess decrease. Lowering flaps increases the camber of the wing and results in more lift for a given velocity. As the flaps are lowered, equivalent parasite area increases. Total drag increases, thrust required increases, and power required increases. Lowering flaps increases lift, allowing the aircraft to be flown at lower airspeeds. The increased drag results in an increase in thrust required and power required, and a shift to the left. Flaps do not affect thrust available and power available. Thrust excess and power excess both decrease. The landing gear causes an increase in parasite drag. The landing gear does not affect engine performance. Lowering the landing gear will increase the thrust required curve, causing a thrust excess to decrease and power excess to decrease. This chart summarizes the direction of the thrust required, power required, thrust available, power available, thrust excess, and power excess curves. Flight control systems. The primary flight controls are the ailerons, elevator, and rudder. They are manually operated using mechanical linkages in the T6B. Ailerons are deflected in opposite directions to create a rolling moment around the longitudinal axis. The elevator is deflected to create a pitching moment around the lateral axis. The rudder controls the aircraft around the vertical axis through a yawing moment. Trim tabs are secondary flight controls. Trim tabs are used to reduce the force that is required on the stick and rudder pedals in order to hold the control surfaces in a desired attitude. Each control surface has an electromechanical trim system associated with it. Trim tabs move in the opposite direction as the control surface in order to hold the control surface in place. Aileron trim. The combined roll pitch trim switch is located on the top of the stick. Left and right movement controls aileron trim. Each aileron has a ground adjustable trim tab for maintenance only. Elevator trim. The elevator trim is once again located on the coolie hat. Fore and aft movement controls elevator trim. Trim nose up for slow air speeds, trim nose down for high speeds. The rudder trim switch is on the front side of the power control lever. Left and right movements control the rudder trim. Rudder trim aid device. The trim aid device assists in maintaining coordinated flight by compensating for airspeed and power changes. The trim aid device will not completely trim the aircraft in yaw. Control balancing is balancing the forces on the control surfaces at the hinge line to prevent flutter and to provide control-free stability. The two types are aerodynamic balancing and mass balancing. The T6B elevator and rudder use the shielded horn for aerodynamic balancing. The T6B uses overhang in the ailerons. Mass balancing. Additional weight is added forward of the hinge line to balance the surface. Now we will talk about the different types of control systems. The T6B uses conventional controls. Controls provide direct link from the stick to the control surface. Thus, aerodynamic forces on the control surfaces are transmitted back to the cockpit through reversibility. This gives the pilot some feedback called control feel. Power-boosted controls provide mechanical linkage with hydraulic, pneumatic, or electrical boosters. These controls are typically found on large aircraft with high control force loading. Decreased feedback, control feel, is provided to the pilot. Full power control system. In a full power or fly-by-wire control system, an electronic or computer-generated signal controls the displacement of the control surfaces. Since no feedback is transmitted to the cockpit, fly-by-wire systems require an artificial means of creating control feel. This is called artificial feel. Artificial feel provides a mean of altering feedback. The T6B uses trim tabs along with a bob weight and down springs. Other aircraft might use computer or mechanically generated feedback. Servo trim tab. Servo trim tabs are typically found on ailerons. The servo trim tab moves in the opposite direction as the control surface in response to control movements. The servo trim tab assists the pilot in moving the control surfaces. Anti-servo trim tab. The T6B uses an anti-servo trim tab to provide artificial feel for the rudder. The anti-servo trim tab moves in the same direction as the control surface, but faster. The further the control surface is deflected, the more difficult it becomes to deflect. Neutral trim tab. The elevator trim tab does not provide the desired type of artificial feel, so the T6B uses a neutral trim tab to provide no artificial feel for the elevator. The neutral trim tab maintains a constant angle to the elevator when the control surface is deflected. The bob weight provides resistance to aft stick motion during maneuvering flight. Downsprings provide resistance to aft stick motion at low velocity. In summary, this is what we discussed to finish out Lesson 2.2.